This example is similar to example 1, but it is even more complicated and builds on the information discussed thus far. A crew is dispatched to repair a jumper on a dead-end 115 kV structure. The original jumper consisted of two ends of conductors, one from each side of the dead-end tower, that were bolted together with a clamp on a temporary basis to meet energization schedules. The task was to replace the temporary connection with a permanent compression sleeve. 315 kV lines connected three separate substations. Line 1 was about 15 miles long, Line 2 was about 30 miles long, and Line 3 was about 25 miles long. These three lines were on common right-of-ways in pairs of two. Lines 1 and 2 were in common right-of-way for about 10 miles. Lines 1 and 3 were in another common right-of-way for about 5 miles. Lines 2 and 3 were in a third common right-of-way for about 20 miles. The steel structure had been painted a few years prior to the incident. Line 1 was de-energized and grounded at both ends, substations A and B, while lines 2 and 3 remained energized. Hence, we see that line 1 formed a long loop consisting of the 115 kV line 1 conductors, station grounds at substation A, station grounds at substation B, and the return path between substations A and B. This loop received induction from line 2 for part of its run and from line 3 for another part of its run. Because of different parallel lengths, loadings, and phase angle conditions, it is difficult to determine which induction source, line 2 or line 3, dominated, and how much each contributed to the induced current. Upon arrival at the worksite, the workers installed two personal temporary grounding cables between the structure and the jumper, one cable on each side of the structure. However, as subsequent investigation revealed, they did not clean off the structure paint carefully before installing the grounding cable clamps, which resulted in a poor electrical connection. They positioned an aluminum ladder from the steel structure arm to the de-energized jumper and climbed down to the jumper to remove the clamp. The first worker was holding onto the aluminum ladder with one hand and steadied the jumper with his other hand. The second worker was also holding onto the aluminum ladder with one hand while using a wrench with his other hand to unbolt the clamp. As he removed the last bolt of the clamp and separated the two sections of the jumper, the second worker was electrocuted. Because the de-energized 115 kV line was grounded at substations A and B, it formed a closed loop consisting of the line conductors, the station grounds, and the ground return. The magnetic field of the other energized 115 kV lines induced current in this loop. When the temporary grounding cables were installed on the structure, the loop was divided into smaller loops. Each smaller loop carried some induced current. However, because the paint was not cleaned off carefully, the contact resistance of the ground cables to the structure was high, thus impeding the current flow through the temporary grounding cables and preventing the establishment of an equipotential zone at the worksite. The temporary grounding cables, in effect, could not perform their intended function. When the second worker separated the jumper sections, the two loops became separated. The small loop consisted of the line to substation A, the substation A ground, the ground return, and the parallel combination of the body of the first worker on the aluminum ladder and the local temporary personal grounding cable on the structure. This small loop carried a small induced current. The large loop consisted of the line to substation B, the substation B ground, the ground return, and the parallel combination of the body of the second worker on the aluminum ladder and the local personal temporary grounding cable on the structure. The large loop carried a large current. And separating the two sections of the jumper allowed current to pass through the second worker's body and caused electrocution. The basic concept was to establish an equipotential zone for the workers. However, several errors compounded to create a hazardous situation. The temporary personal grounding cables were not installed properly on the painted structure. The paint was not removed carefully to ensure good electrical contact between the cable clamp and the structure. This raises an important point. Do not rely on mechanical contact to carry current. Mechanical contact often results in poor electrical contact since the contact resistance can be high unless proper precautions are followed, and in this case, cleaning off the paint. Also, mechanical contact can become loose due to movement. Installing a temporary jumper across the clamp prior to removal would have provided an alternative low-resistance path for the current and would have helped in establishing an equipotential zone around the workers. Unfortunately, hazardous conditions would still remain if an aluminum ladder were used and if the temporary personal grounding cables were not installed properly. Therefore, it is important to consider all factors and equipment at the worksite.